My name's Alexa Van Eaton, Vaneaton, and I'm a research geologist here at the U.S. Geological Survey Cascades Volcano Observatory.
And tell us a little bit about your specialty and what you focus on here.
Sure. So I work on the dynamics of eruptive processes, volcanic plumes, pyroclastic density currents, how we can monitor those processes, and how those processes are recorded in the geologic record.
And what can you tell us about how you've applied that and what we've learned about what happened during the big 1980 eruption?
The May 18 eruption of 1980 is known internationally as one of the most important eruptions of the modern era. And the reason for that is that there was amazing monitoring before, during, and after the eruption, and the eruption plume transported its blanket of ashfall entirely over a landmass. And that's unusual. Most eruptions deposit their ash, at least somewhat, in the ocean. So the May 18 eruption provides an incredibly complete and rich data set for understanding how explosive volcanoes transport ash across the landscape. And so one of the aspects I'm really interested in is going back to the geologic record, so the layers that are recorded from May 18, to learn more about what happened on a minute-by-minute basis so that we can improve our models of ash transport and have a better, more effective ash transport forecast model for the future.
And when you talk about that ash layer blanketing a landmass, are we talking about the state? Are we talking about the continent? Or are we talking globally?
So the May 18 ashfall deposit extended all the way across the American West, and there were even eyewitness accounts of some ashfall out to the East Coast. So of course the airborne ash transported globally, but the footprint of the fall deposit covered almost the entire continental US. And so that enormous ashfall blanket provides an amazing amount of data for scientists to connect a geological deposit with the processes that happened at the volcano.
And what are some of those processes that happened that you can tell us about?
So Mount St. Helens May 18 is unusual in that so many different things occurred over the course of the 9-hour eruption. Not only was there a blast, an explosion of a dome that blasted out sideways and produced an incredibly powerful pyroclastic density current, but there was a high eruption plume that lasted for several hours, reached 17 kilometers above sea level. And the pyroclastic flows that issued from the volcano also lofted ash into the atmosphere that actually reached up to 37 kilometers high. So there were multiple different dynamic processes happening that all contributed to that ashfall deposit, that blanket that covered a lot of the US continent. So it's an incredible place for us to go back and tease out what we know happened, what eyewitness observers recorded, what monitoring instruments recorded, and connect that to the layers in the geologic record. It provides a sort of Rosetta Stone for us to be able to forensically reconstruct what eruptions do and how they record that in the stratigraphy.
And this, of course, was not Mount St. Helens' first eruption. Can you look back even further back in time and see what happened in previous eruptions?
Absolutely. So being able to look back into the pre-1980 geologic record of Mount St. Helens shows us the incredible diversity of this volcano, not only compositionally, different magma types, but different explosive styles and tempos, and even periods of dormancy. So what we can do by using the May 18 record and the detail that we can observe connecting monitoring and the geology is to then go back into the pre-1980 record, up to 300,000 years ago, but in the most detail is eruptions that have happened over the past 4,000 years, and reconstruct layer by layer what has happened over the geologic history of Mount St. Helens.
Can you go a little bit more into detail about the different types of eruptions you've observed from these different geologic periods?
So what's happening now at the volcano in terms of the last couple thousand years has dramatically changed over time. So around 2,000 years ago, there was a completely different style of volcanism at Mount St. Helens. It was not high plumes, explosive ash-forming types of eruption plumes. There were lava fountains. There were extensive sheets of basaltic lava flows, more like what you see in Hawaii today. And previous to that, 3,000 years ago, things were different then. Instead of having a single edifice, there were multiple cones producing pyroclastic flows and little ash plumes that sort of, created a composite dome center. And so the shape of the volcano, the style of eruption, the composition of the magmas have all dramatically changed, even over just the past 3,000 to 4,000 years at this volcano. So it really is a special place in terms of the diversity of eruption style and magma composition compared to other volcanoes in the world and in the Cascades.
And the volcano woke up a little bit again in the early 2000s. How did what came out during that eruption period compare to what was seen in the 1980 eruption?
So the volcano reawoke from 2004 to 2008, and most people don't think about the last eruption of Mount St. Helens being that recent, but in fact, 2008 was the last time it erupted. So that eruption style was quite different from May 18, 1980. There were small domes and dome collapses that were much more confined to the area around the volcano. There were ash plumes, but not so extensive that they majorly disrupted, global aviation. So a much smaller scale of activity, and yet really important for us to monitor and to keep track of, because that gives us a good indication of what we may see when Mount St. Helens erupts next. So we don't necessarily expect at this point to see another May 18 occur. We expect to see something more like what we saw 2004 to 2008, with dome growth, dome collapse, and smaller ash plumes. But this is where the monitoring comes in, and the geology, really being able to observe day by day what the monitoring data are telling us and what we see happening at the volcano to change that potential forecast.
And talking about today in your monitoring, what kind of activity are we seeing right now?
So right now, Mount St. Helens is at a background level of activity. That means there's seismic activity, there are gas emissions, but nothing that the current background level of monitoring suggests is above sort of typical Mount St. Helens level of activity. But what's really important for that effort is having a continuous and consistent data stream to make sure that we're keeping track of any changes and being able to compare that to a long record of monitoring to be able to distinguish when there is an uptick in seismicity or gas emissions or deformation that might signal a change in magma movement.
And what are some things that you specifically with your specialty are looking for or watching as an indication that something might be changing?
So as a team here at the Cascades Volcano Observatory, we work together to discuss the monitoring data every single week. So we have a rotation of duty scientists, and we discuss what are the gas emissions doing this week? What are the seismic observations telling us this week? And then what can we as geologists do to prepare for the next big eruption at Mount St. Helens? So we have meetings to think about a strategy for where we would collect ash in the next ashfall event, how we would structure our site deployment to best collect the ash particles that will tell us the story of magma movement in advance of the next phase of activity.
And kind of looking back at the geologic timeline of volcanic activity in the Cascade Range as a whole. Can you talk a little bit about how the activity at Mount St. Helens compares to other volcanoes in our region?
So everything we can see at Mount St. Helens today, the entire shape of the edifice, developed over just the time since the pyramids of Giza, over the last 4,000 years. So it's an incredibly young volcano. It's an incredibly active volcano compared to the other Cascades volcanoes, compared to global volcanoes. So for this type of stratovolcano, it has an unusual number of explosive eruptions in the young geologic record. So this is where people going back to study the layers in the geology and the scientists who study the monitoring data really come together, because we can connect our eruptive frequency data and our eruption process data to help interpret what the monitoring signals indicate in near real time.
And what have we learned, not just about like Mount St. Helens possibilities in the future, but about the other volcanoes and their possible future activity?
Mount St. Helens is an outlier in the Cascades in terms of how frequently it erupts explosively. But we have a lot of other potentially hazardous volcanoes in the Cascades. One little known volcano, a volcano that doesn't have such a prominent skyline shape, is Glacier Peak in the North Cascades in Washington. And behind Mount St. Helens, Glacier Peak volcano is the second most active explosive volcano in the Cascades. So there's a lot that we can learn from Mount St. Helens, reading those layers like a book at Mount St. Helens, and then going to a lesser known volcano like Glacier Peak to understand what the layers there tell us about the frequency of explosive and hazardous eruptions.
And the images of the 1980 eruption were really quite striking, and that explosion and the pyroclastic cloud. So some people might be wondering, if there was another eruption like that, how much could it actually impact the immediate area around it, and how much we pay attention to how close we're building to volcanoes like that?
Well, at present, Mount St. Helens is in a national volcanic monument, so there's really limited building that's possible within the devastated area. So that's one key feature. That's a zone for a reason. But that said, this is why the U.S. Geological Survey has active and continuous monitoring of the volcano, so that day by day, as the data comes in, we can provide the science information to inform land managers what is the most likely scenario for eruption hazards, to make sure that they can get people out of harm's way, make sure that people aren't working in the area during the next phase of unrest and eruption. Now, Mount St. Helens is not like a Pompeii situation where pyroclastic flows are going to inundate an entire city. That's not the scale of volcanism that we see at this volcano. But as we saw in May 18, and even during 2004 to 2008, the ashfall footprint has an enormous impact on aviation. Of course, airplanes can't fly through volcanic ash. It damages the engines. And there are downstream effects of the sediment load in the watershed that have major impacts on downstream communities. So these two features, the downstream and the downwind effects, are incredibly important even for smaller scale eruptions at Mount St. Helens, which is why we keep such a careful and close eye on what's going on there.
Are you able to talk a little bit more about those downstream effects, how the earth changed, how the ash deposits really changed the landscape in that eruption, and how it's kind of settled down or changed or evolved in the years since?
The area north of Mount St. Helens is unrecognizable now compared to how it was before the May 18 eruption. And the sediment load in the watershed in the North Fork of the Toutle and downstream is more than an order of magnitude greater than it was before the eruption. And that has enormous impacts on how people handle that extra sediment load. And it teaches us that eruptions can have downstream impacts for decades after they erupt. You know, we think immediately about the people who were impacted by the eruption, the people who were killed by the eruption. But decades of significant downstream watershed reorganization is something that occurs during big eruptions like this. So that's also something that Mount St. Helens has taught us about not just an immediate impact, but something that can last for a lifetime.
Can you tell us a little bit about how technology has evolved since 1980, the kind of tools that you have at your disposal, just, how far we've come since then?
So we have a number of really important new technological advances that will help us in the next phase of eruption at Mount St. Helens. For example, we have new satellite sensors that would allow us to do much improved near real-time monitoring of any ash clouds that are in the atmosphere and pyroclastic density currents that are moving along the ground, clouds of ash that hug the ground and are super hazardous. We also have new lightning sensors that can help us detect electrical activity in volcanic clouds. This is one of the new and emerging areas of science that can help us detect when eruptive activity is happening, how long it's lasting, and at what intensity. So we do have new tools, and at the same time, some of the old school tools that were available in 1980 and before are still really crucial. Having scientists that are boots on the ground, just using your eyes and your ruler and your sample bags and taking photographs of what is preserved after an eruption. All of that is fairly unchanged, but incredibly fundamental and important basic observations to support decades of science that would come after.
Can you talk a little bit about how the different USGS stations around the country kind of share knowledge? We have, Kilauea, we have potential eruption on the horizon in Alaska. So, how do you do this knowledge sharing throughout your community?
So the U.S. Geological Survey has 5 different volcano observatories centered around different volcanically active areas of the U.S. So that's the Hawaiian Volcano Observatory, Alaska, the California Volcano Observatory, here in the Cascades, and Yellowstone. So all of us work closely and carefully together. In fact, during the 1980 eruption at Mount St. Helens, scientists from Hawaii came over to the Cascades and were deployed here to work on the eruption in 1980. Likewise, when Kilauea had a significant eruption in 2018, Cascades scientists came to Hawaii to help with their response. So there's an enormous amount of knowledge sharing. We have a lot of meetings to discuss the data and think about ways that we can work together and really leverage all the existing technology at our disposal to best monitor and forecast the hazards of eruptions.
It's very easy to forget that we have Mount St. Helens, we have Mount Hood, just right in our own backyard. So is there anything you would like to share just for the average everyday person who lives around these amazing mountains?
I think that's a really important point, that we are surrounded by beautiful, awe-inspiring volcanoes, and just remembering that all of these volcanoes are still considered active geologically. If they had an eruption in the past 10,000 years, that's an indication that they could wake back up again. And so the key here is making sure that we have scientists monitoring the activity levels of these volcanoes so that if and when anything changes, we'll be able to provide that science content to keep people out of harm's way.
Is there anything I haven't asked that you would like to include or you think people should know?
There was one question you sent us that I thought about, that I got kind of excited about, which was, is there anything surprising that we're learning from the May 18 eruption? Like what the 1980 eruption teaches us now that's surprising. And I've been going back to the deposits from May 18 pretty much every year for the past 10 years, and you'd think, as a non-specialist, that you would learn all there is to know in that amount of time. But every single time I visit the stratigraphy of the May 18 eruption, it teaches me something new. And just this last summer, examining the deposits in detail and looking at sort of millimeter by millimeter scale through the layers, we saw something new, which is to see that there are little tiny volcanic hailstones that formed in the eruption cloud in places that we never knew had happened, because there weren't observations that we were able to get directly in the cloud, because of course those people perished. So being able to see what happened layer by layer in the most close proximal deposits can help us better reconstruct what occurred in May 18 and what could happen during the next eruption.
I really love that answer. Thank you for remembering the question. It just made me think of another one.
Yeah.
Can you talk about a little bit about, we're talking about deposits and all these layers. Can you talk about how thick some of those deposits were, just like how much came out of that eruption?
So the thickness of the deposit varies enormously. There are areas in the canyons right on the pumice plain north of the volcano where you're in a deep canyon of thick pyroclastic flow deposits. You can't, several hundreds of feet high. So there are places where you can't even see the bottom yet. It's so thick. And there are other places where the blast deposit from the lateral blast of the cryptodome is only about this thick or one inch thick. And yet it was still deadly in those places for 57 people. So even where the deposit is tiny and doesn't look like it would have done much, it is actually representing a hazardous and deadly pyroclastic density current. So this is a jar of volcanic ash from May 18, 1980. And as you can see, this is the material that was falling on states downwind of Mount St. Helens all the way through Montana, Colorado. And it doesn't look like much. It's just very fine-grained particles. It looks like sand. But this stuff is really different from wildfire ash that we also get a lot of in the Pacific Northwest. The reason it's different is that this is pieces of rock, and it's abrasive, so it doesn't break down the way wildfire ash does. When you have a layer of wildfire ash, it degrades biologically, and so it eventually just sort of disappears. Volcanic ash is really hard to get rid of. So after May 18, there was an enormous cleanup activity of folks downwind who had to deal with this stuff, covering their roofs and their roads and their cars. The other thing about this is that when these tiny particles of ash go through a jet engine, the particles melt in the engine and refreeze and re-solidify on the engine. And that can cause engine flame out. It can cause enormous damage to the engine and even aircraft crashes. So a huge part of what we do is monitor the explosive activity that results in volcanic ash so that we can provide the information to keep aircraft out of ash clouds. So in 1980, we didn't have computer models that could forecast where an ash cloud was going to go and who would be hit by the volcanic ash. So after May 18, using the data collected from that eruption, we now have computer models like ASH 3D that can forecast and numerically compute the direction, the transport, and the sedimentation of clouds that carry this ashfall. You can go to the website, the U.S. Geological Survey website, and there are ASH 3D simulations running every day for our active volcanoes to see where ash would go if it erupted today.
And let's say the ash fell on an urban area, on people's cars, on your house, and sewer systems. What happens when it gets wet?
The ash gets particularly heavy when it's wet, and so that can be really burdensome to structures. And at the same time, one very useful method for getting volcanic ash off the windscreen of your car is to not give in to the temptation of wiping it or scrubbing it off the way you could wildfire ash, but to spray it off with a hose. Because this ash is extremely abrasive and it would scratch your windscreen. So instead of scraping it, like snow or ash, wildfire ash, use a hose and spray it off, or a water bottle. But for areas that get a huge amount of ash, like several inches of ash, when it's mixed with water, it becomes a muddy slurry. It's really heavy. It's incredibly disruptive, particularly on the roads. It changes, makes the roads less safe to drive on. It's very slippery. And so there are several significant issues to the community dealing with the after effects of ashfall for weeks to months and even longer.
So the ash samples that you're working with, were they all ones that were collected within the days and the weeks after the 1980 eruption, or are you still collecting samples today from that same event?
So we do have samples that were collected in 1980 just after the eruption. And we have samples that we collected just last summer. And those types of samples provide different information. The ones that were collected right after the eruption in 1980 are extremely valuable because they provide a pristine sample that has never been rained on. That's really useful for understanding the chemical adsorbed components called leachates that are stuck onto the ash particles and can wreak havoc to downwind communities. Likewise, the samples that we've collected more recently, they're rained on, and so they don't provide the sort of surface chemistry, but we can do more detailed studies to compare layer by layer what we can learn about that history of the 18 May eruption.